Global energy transition is stalling at the physical grid level. Lead times for utility-scale transformers have surged from 30 weeks in 2020 to an estimated 190 weeks in 2026. This 533% increase is driven by a structural deficit in grain-oriented electrical steel, or GOES. Global demand for this specialized alloy is expanding at a 7.2% compound annual growth rate. Meanwhile, production capacity is growing at less than half that pace. The supply-demand crossover in late 2022 depleted global buffer inventories. Utilities must now place orders up to 4 years in advance of project execution. The supply chain for grain-oriented electrical steel is highly consolidated and geographically vulnerable. East Asia controls over 66% of global production capacity, with China alone representing over 43%. High permeability, or high B-grade steel, is even more concentrated. Japan and South Korea yield the highest quality, with 85 to 90% of their output meeting high B standards. This leaves Western buyers dependent on a highly localized East Asian supply chain. The United States relies on a single domestic facility in Pennsylvania. This plant produces only 250 kilotons annually, of which only 40% meets high permeability specifications. This creates a single point of failure for Western grid modernization. Substituting lower-grade metals to bypass this bottleneck is physically and regulatorily impossible. Replacing grain-oriented steel with non-oriented electrical steel increases core energy losses by over 250%. This violates upcoming Department of Energy efficiency standards. While laser-scribed high-B steel minimizes core loss to 0.55 watts per kilogram, it requires specialized thermal treatments that increase production costs by 40%. This process is difficult to scale quickly. Amorphous metal alloys offer lower core losses but are highly brittle and lack the magnetic saturation required for large-scale utility applications. The physical laws of electromagnetism dictate that there is no cheap or rapid alternative to high-grade electrical steel. The primary bottleneck in the nuclear fuel cycle is not mining or enrichment, it is chemical conversion. Converting yellowcake into uranium hexafluoride gas is a thermodynamic prerequisite for enrichment. Decades of underinvestment have left the West structurally dependent on Russia. Russia's state-owned Rosatom controls approximately 38% of global conversion capacity. In 2024, global demand of 65,000 metric tons of uranium outstripped operational capacity of 62,000 metric tons. This deficit has forced a continuous drawdown of commercial inventories since 2018. Western capacity is projected to expand by nearly 35% by 2030. However, this expansion is too slow to allow immediate decoupling. Without sustained demand-side rationing, the Western nuclear fleet remains highly vulnerable to Russian supply disruptions. Western conversion capability is highly consolidated and fragile. Only 3 commercial facilities operate in the Western Hemisphere. Orano in France and Cameco in Canada represent over 81% of this active capacity. The United States has only one domestic source, the Conver-Din Metropolis plant. Metropolis operated at just 65% of its 7,000 metric ton capacity in 2024 due to technical restart delays. This leaves the domestic fuel cycle without any operational buffer. Western facilities face an average operational efficiency gap of over 17%. This deficit is driven by equipment aging, regulatory shutdowns, and hazardous chemical handling. The highly corrosive nature of fluorine gas prevents rapid, modular scaling of these facilities. This physical bottleneck has triggered an acute pricing shock. Spot conversion prices surged by 317% between 2019 and 2024. Prices escalated from $11.50 to $48 per kilogram of uranium. Securing conversion services now requires unprecedented lead times. The average wait time expanded from 12 weeks in 2019 to 96 weeks in 2024. This backlog indicates a severe deficit in active chemical processing pipelines. Long-term contract prices have adjusted upward to $36 per kilogram. This shift reflects utility expectations of structural deficits lasting through the decade. The transition to Western fuel independence will be slow, expensive, and highly constrained by physical chemistry. The Rhine River is Western Europe's primary industrial artery, carrying over 170 million metric tons of cargo annually. Its most critical bottleneck is the Cobb choke point. Here, water depth directly dictates the cargo capacity of the entire inland fleet. A gauge height of 80 centimeters forces a standard class Va barge to shed 60% of its payload. This is necessary to maintain a safe 30-centimeter underkeel clearance. At extreme low water levels of 40 centimeters, effective capacity drops to just 15%. This forces operators to use 26.7 vessels to move the volume normally carried by 4. Below 30 centimeters, commercial navigation faces complete physical suspension. This hydrological bottleneck is no longer an occasional disruption. The frequency of severe low water days at Cobb is accelerating rapidly. 2018 and 2022 recorded 92 and 78 low water days, respectively. The historical 20-year average is just 18 days. This shift has direct macroeconomic consequences for the Eurozone. A continuous 30-day drop below 80 centimeters correlates with a 0.5% reduction in German quarterly industrial output. Projections through 2030 suggest 40 to 50 low water days will become the annual baseline. Alternative transport networks lack the capacity to absorb this displaced cargo. Substituting a single 3,000-ton barge requires 2.5 block trains or 120 heavy-duty trucks. The European rail and road networks have no such spare capacity. During low-water crises, barge spot rates surge by 284%. Surcharges push costs from €12.50 to €48 per ton. Diverting this freight to roads also increases carbon emissions by 520%. The physical reality of European geography means there is no viable substitute for the Rhine. The expansion of the lunar economy is colliding with a rigid terrestrial communications bottleneck. NASA Deep Space Network is operating beyond its physical capacity limits. In 2024, total requested tracking hours reached 172,100 hours. Maximum operational capacity limited allocations to just 115,300 hours. This mismatch resulted in a 33.0% request deferral rate. By 2030, projected tracking demand will scale to 255,000 hours. This will drive the rejection rate to an estimated 47.1%. The structural deficit is worsened by the physical degradation of the ground infrastructure. The primary 70-meter antennas require up to 45 hours of unscheduled maintenance every month. This further reduces available tracking windows for critical missions. High-priority human spaceflight is systematically crowding out scientific exploration. Lunar and Artemis-related missions increase their share of total network allocations from 11.7% in 2020 to over 36% in 2024. This rapid scaling directly starves deep space science of bandwidth. Allocations for planetary exploration and outer planet probes declined from 68,000 hours to 51,000 hours over the same period. This represents a 25.0% reduction in tracking support. Artemis missions require near-continuous coverage of 12 to 14 hours daily per spacecraft. Non-flagship robotic missions are left with fragmented, suboptimal communication windows. This structural prioritization threatens the return of scientific data from the outer solar system. The congestion is highly concentrated in specific electromagnetic frequencies. Ka-band frequencies are critical for high-resolution imaging and Artemis telemetry. Yet, they suffer the lowest allocation efficiency at just 54.8%. This results in an estimated loss of 850.2 gigabytes of scientific data monthly. The Workhorse X-band remains heavily congested. 71.2% allocation efficiency forces spacecraft to store data on board for extended periods. This operational workaround increases the risk of critical memory overflows. Experimental optical laser communications offer massive throughput but remain highly vulnerable to atmospheric attenuation. They currently achieve only a 15.0% operational allocation efficiency. Terrestrial radio frequency infrastructure remains an unavoidable single point of failure for the space economy. The federal target of deploying 30 gigawatts of offshore wind capacity by 2030 is mathematically unviable under current maritime law. The Merchant Marine Act of 1920, known as the Jones Act, requires all domestic maritime transit to use U.S.-built, flagged, and crewed vessels. This protectionist framework isolates the domestic market from the global installation fleet. To meet the 2030 target, the United States requires 5 to 6 dedicated wind turbine installation vessels operating continuously. Yet, domestic compliant supply remains at zero. The delayed delivery of the sole domestic new build, the Charybdis, leaves a 100% deficit during peak construction years. Building compliant vessels domestically is cost prohibitive. A U.S.-built installation vessel costs $625 million, This represents a 115% premium over South Korean shipyards and a 184% premium over Chinese shipyards. Domestic build times average 60 months, double the 30 months required in East Asia. This delay stems from a lack of specialized dry dock infrastructure and heavy marine crane supply chains. Despite the capital premium, the domestic vessel's crane capacity of 2,200 metric tons lags behind international standards. Foreign shipyards routinely deliver vessels with up to 3,000 tons of lift capacity. This technical gap renders domestic builds obsolete before they launch, as turbine sizes scale past 15 megawatts. To bypass the vessel deficit, developers rely on feeder barge logistics. This workaround utilizes U.S.-flagged tugs and barges to ferry components to stationary foreign vessels offshore. This methodology increases daily operational costs to $485,000, a 29.3% premium over direct installation. The process requires 3 specialized tug and barge sets, adding $95,000 in daily lease costs. Crucially, weather-related risk premiums escalate by 350%, transferring 400-ton nacelles and 100-meter blades between moving hulls in open ocean swells introduces severe physical hazards. This regulatory bottleneck mirrors the shipping crises of World War I. Protectionist constraints have once again crippled strategic infrastructure deployment. The transition to high-energy density batteries has forced a fundamental shift in nickel metallurgy. High-purity Class 1 nickel, historically sourced from deep magmatic sulfide deposits, is depleting rapidly. To meet demand, the supply chain has pivoted to high-pressure acid leach processing of low-grade laterite ores. This technological shift concentrates production in low-cost, high-carbon jurisdictions. Indonesian operations offer a massive cash cost advantage, clustering between $11,500 and $12,200 per metric ton. However, this cheap supply relies on captive coal-fired power grids. The resulting carbon footprint averages 22.5 to 28.0 metric tons of carbon dioxide equivalent per ton of nickel. This is 5 to 7 times higher than Canadian sulfide operations. Western electric vehicle manufacturers face a direct conflict between cost optimization and carbon accounting standards. Geographic concentration has followed this metallurgical pivot. Indonesia's share of global nickel supply expanded from 12% in 2015 to 52% in 2024. This rapid expansion has systematically marginalized traditional sulfide ore producers. By 2030, Indonesian laterite-based production is projected to command 63% of the global market. This consolidates supply chain control within a single geographic jurisdiction, heavily reliant on Chinese capital and technology. The displacement of non-Indonesian sulfide mines has eliminated the market's supply buffer. Western buyers seeking low-carbon, ESG-compliant nickel face an increasingly illiquid and expensive market. The physical reality of nickel geology has created a near monopoly. The environmental trade-offs of this transition extend beyond carbon emissions to physical waste. High-pressure acid leach plants generate 1.5 metric tons of wet tailings for every ton of nickel produced. In equatorial Indonesia, deep-sea tailings disposal is restricted due to marine ecological risks. Operators must rely on dry stacking. This storage method presents severe risks in a region characterized by high seismic activity and annual rainfall exceeding 3,000 millimeters. A catastrophic tailings failure remains a constant operational and ecological threat. Alternative processing routes do not solve this dilemma. The pyrometallurgical nickel pig iron to matte pathway reduces physical tailings, but emits 65 tons of carbon dioxide per ton of nickel. High-pressure acid leach remains the dominant economic choice, but its ecological debt continues to compound. Advanced microchip fabrication relies on deep ultraviolet and extreme ultraviolet lithography. These systems require Excimer lasers. These lasers depend on high-purity neon gas as a primary buffer. Historically, this gas was a cheap byproduct of Soviet-era steel manufacturing in Ukraine. The war in 2022 severed this supply chain instantly. This forced a rapid, capital-intensive realignment of global purification capacity. China quickly captured 55% of the market by 2023. Meanwhile, the United States and South Korea are aggressively reshoring purification infrastructure to secure their domestic semiconductor fabs. Loss of Ukrainian purification plants in early 2022 triggered an immediate supply shock. Spot prices for 5N purity neon surged from $2.50 to over $54 per liter. This represented a 2,060% increase in just 2 quarters. Global operating capacity contracted by half, falling to 380 metric tons per year. This extreme volatility exposed the fragility of just-in-time chemical supply chains. While global capacity has since recovered to 950 metric tons, structural premiums persist. Localized processing in the West remains far more expensive than legacy Eastern European operations. Resolving this bottleneck is constrained by severe engineering and thermodynamic realities. Neon exists in the atmosphere at only 18.2 parts per million. Capturing it requires massive air separation units integrated directly into steel mills. Refining this crude gas to 5N purity requires specialized cryogenic distillation columns operating below -246 degrees Celsius. Building an integrated system requires up to $21 million in capital expenditure. It also demands up to 42 months of lead time. Furthermore, the purification process is highly energy-intensive, consuming up to 500 megawatt-hours per metric ton. These physical barriers prevent rapid supply adjustments. The disruption of deepwater Black Sea maritime routes forced an immediate, inefficient pivot to inland waterways. Danube River export volumes surged from under 0.2 million metric tons per quarter in 2021 to a peak of 2.4 million metric tons in the third quarter of 2023. Bypassing traditional maritime infrastructure imposed a severe economic penalty. The transit cost premium for routing grain via the Danube peaked at $41.50 per metric ton. This represents an 8-fold increase over the pre-conflict baseline. While the partial reopening of Black Sea ports in 2024 reduced Danube volumes, a persistent premium of $24.50 per ton remains. This cost floor highlights the structural inefficiency of inland river logistics compared to direct maritime shipping. The primary physical barrier to this overland pivot is the Breakov gauge at the Ukrainian-European border. Ukraine operates on the Soviet standard 1,520mm broad gauge rail system. Neighboring European states use the 1,435mm standard gauge. This incompatibility requires either mechanical bogie exchanges or physical transshipment of bulk grain. Physical transshipment doubles processing latency, requiring up to 36 hours per train at major crossings like Vadalseirt. This delay restricts daily throughput to just 120 wagons. The Port of Galati bypasses this bottleneck by running a broad gauge line directly into Romanian territory. This infrastructure reduces processing times to 8 hours and boosts daily capacity to 220 wagons. Elsewhere, lack of specialized transshipment infrastructure creates multi-day rail backlogs. Once grain reaches the Danube, it encounters a severe maritime bottleneck at the Sulina Canal. This narrow channel is the primary deepwater outlet to the Black Sea. In September 2023, the active vessel queue peaked at 145 vessels. Average waiting times reached 18.5 days for inbound barges. Daily transit capacity only expanded from 15 to 24 vessels over 30 months, despite emergency dredging. This capacity deficit drove vessel demurrage costs to $15,000 per day. This crisis mirrors the late 19th century grain bottlenecks in the American Midwest. Incompatible rail gauges and transshipment monopolies at Chicago then forced federal intervention. Today, physical geography and rigid infrastructure continue to dictate the limits of global food security.